Hello students. Today we will look into the refining of metals. Firstly, let us see about the electrochemical principles involved in metallurgy and how aluminium can be profitably extracted by the electrochemical process. Then we will look into the various other processes like distillation, liquation and the electrolytic refining. The electrochemical process is carried out for most reactive metals like sodium, potassium, calcium and magnesium. In metallurgical processes, two principles are involved. One is thermodynamic principle, which we discussed earlier. Second is electrochemical principle, which will be dealt today. For active metals like sodium, potassium, calcium, magnesium, aluminium, the reduction by carbon is thermodynamically not feasible. Hence, the extraction or reduction of metal oxide is done using electrochemical principles. During the electrochemical principle, the metal ion in the fused or the solution form is reduced by a suitable reducing agent or by electrolysis. Now let us look at the word electrolysis. In the word electrolysis, electro stands for electric current while lysis stands for splitting. The substance that is being used in an electrolytic process will be called as an electrolyte, which will always be in the fused or in the molten form. The anode, which is a positive electrode, is otherwise called as the oxidation electrode, wherein loss of electrons takes place. At the cathode, which is otherwise called as the reduction electrode, gain of electrons takes place. According to thermodynamics, change in the Gibbs free energy delta G for the electrolysis process is given by delta G naught is equal to minus NF E naught, where delta G naught is a change in the standard free energy. N stands for the number of electrons transferred during the reaction, and F stands for Faraday, which is a constant, and E naught is a standard electrode potential of the redox couple. Let us see how highly reactive metals and less reactive metals are related by the expression delta G naught is equal to minus NF E naught. For highly reactive metals, E naught value becomes more negative. When E naught becomes more negative, minus into minus will become positive. So, delta G naught becomes positive. When delta G naught becomes positive, it is a non-spontaneous reaction and the reaction is not feasible. Now, when we have the less reactive metals, the value of E naught will be positive. And when E naught is positive, plus into minus, delta G naught value becomes minus, negative. So when delta G naught is negative, such a kind of a reaction is spontaneous and feasible reaction. So if it is a feasible reaction, then reduction will occur or take place. During electrolysis, the redox reaction is planned in such a way that the EMF of the net redox reaction is positive. In an electrochemical process, both oxidation and reduction occurs, so it is called as a redox reaction. And in the redox reaction, E naught value will have to be positive, and only then delta G naught value will become negative and it will become a feasible reaction for reduction to occur. In simple electrolysis, at the anode, N plus ions are formed which gets deposited at the negative electrode, that is the cathode. Generally remember that more reactive metals will go into solution. So, when a more reactive metal such as copper is added to a solution of less reactive metal such as Ag+, the more reactive metal copper will go into solution and Ag silver gets precipitated. In example 2, zinc is more reactive than copper. Thus, when zinc is added to a solution containing copper 2 plus ions, zinc goes into solution precipitating copper. Let us look at the electrochemical extraction of aluminium. In this method, electrolysis is carried out in an iron tank lined with carbon, which acts as a cathode. The carbon blocks immersed in the electrolyte acts as the anode. A 20% solution of alumina, which is obtained from the bauxite ore, is mixed with cryolite, which is in the molten form, and 10% of calcium chloride is also added to the solution. The reason why calcium chloride is added to this molten solution is because calcium chloride lowers the melting point of the mixture. The fused mixture is maintained at a temperature above 1270 Kelvin, and chemical reactions takes place in this process. The ionization of alumina first is represented here. Alumina, which is Al2O3, gets split up into 2Al3 plus and 3O2 minus during this electrolysis process. And during this electrolysis, there are reactions which take place at the cathode where reduction and gain of electrons occurs, and there are reactions that takes place at the anode where oxidation or loss of electrons occurs. Let us see what are the reactions that take place at the cathode. At the cathode, the aluminium ions, which are positively charged, combines with 6 electrons to form 2Al, which is in the liquid form. There is a gain of electrons that takes place at the cathode. Now, the oxygen ions, O2 minus ions, they go to the positively charged electrode, that is the anode, and gives up the electrons, or loss of electrons takes place, and oxygen in the gaseous form is obtained. And since oxygen in the gaseous form is O2, to balance this, we will write it down as 3O2, and on the reactant side it becomes 6O2 minus. So 6O2 minus, the charges will be, number of electrons will be 6 into 2, 12 electrons, which are written on the right hand side of the equation, denoting that loss of electrons are taking place. Since carbon acts as an anode, the following reactions also take place. Carbon reacts with oxygen ions O2 minus and can form carbon monoxide or carbon dioxide with the release of electrons. Due to the above redox reactions, the anode is slowly consumed during electrolysis, and at the cathode, pure aluminium is formed and settles down at the bottom. The net electrolysis reaction can also be denoted as 4Al3 plus in the molten state plus 6O2 minus in the molten state combines with 3 atoms of carbon in the solid state from the anode and forms 4Al, which is deposited at the cathode, plus 3 carbon dioxide in the gaseous form being released at the anode. Let us go through this evaluation question. Metallic sodium is extracted by the electrolysis of brine, which is aqueous NaCl. After electrolysis, the electrolytic solution becomes basic in nature. Write the possible electrode reactions. Now to solve this, sodium chloride on electrolysis ionizes into Na plus and Cl minus ions. The more reactive a metal, the less readily its ions is reduced on the electrode surface. H2O, which is present along with the sodium chloride in the brine, ionizes into H plus ions and OH minus ions. Since H plus ions will go to the cathode and hydrogen atoms in the gaseous form will be formed, and it is written as H2, here we write it as 2H plus. So the protons are written as 2H plus, and to balance the equation we write it down as 2H2O on electrolysis splits up into 2H plus plus 2OH minus. The positively charged Na plus ions and the protons will go to the cathode where reduction occurs due to the gain of electrons. The two sodium ions will take up 2 electrons and forms 2Na, which is metallic sodium. Similarly, the two protons gains 2 electrons and forms hydrogen gas, which is evolved at the cathode. Now at the anode, which is positively charged electrode, oxidation takes place and loss of electrons also occurs. 2Cl minus in the aqueous form loses 2 electrons and forms chlorine gas. This can also be written as, another way of writing it down will be 2Cl minus 2 electrons, which tells us there is loss of electrons taking place there and chlorine gas is evolved. So chlorine gas is evolved at the anode, hydrogen gas is evolved at the cathode. The overall reaction for brine will be 2NaCl in the aqueous form combines with 2H2O in the liquid form to form 2NaOH in the aqueous form plus hydrogen gaseous form plus chlorine in the gaseous form. The OH minus ions combines with the Na plus ions to form NaOH. So the solution will be basic in nature. Let us discuss about the refining processes in metallurgy, which involves various methods, of which we will see about distillation, liquation and electrolytic refining today. Let us see what refining is. Removal of impurities such as unreacted oxide ore, other metals and non-metals associated with the isolated crude metal is called as the refining process. Refining of crude metal gives the metal in the purest form. Let us talk about distillation. Let us see an example of distillation that we observe in our home every day. We know that salt in water tastes salty. When this solution is being heated with the lid over it, we see that the water vapor is formed on the lid, which on condensation can give back the water. This water is pure from sodium chloride, making it tasteless. This is an example for simple distillation. Now let us look at the distillation which is being done in the refining process. We use low boiling volatile metals like zinc with a boiling point 1180 Kelvin, mercury whose boiling point is 630 Kelvin, having impurities of high boiling point. During this process of distillation, the impure metal is heated where it undergoes evaporation and the metal changes over into the vapor phase, which is condensed, and on condensation pure metal is obtained and the impurities are separated. Now we will see the next method in the refining process, which is liquation. Liquation is used for removing impurities with high melting point from metals having relatively low melting point like tin, whose melting point is 505 Kelvin, lead, whose melting point is 600 Kelvin, mercury, whose melting point is 234 Kelvin. In this liquation process, the crude metal, which contains the impurities, is heated at a very high temperature in a reverberatory furnace, having a temperature above the melting point of the metal in the absence of air. Now it forms a fusible liquid. This fusible liquid is allowed to flow on a sloping surface, where the impurities are left behind in the reverberatory furnace and the molten pure metal is collected and later is solidified to get the pure metal. The next method in the refining process is electrolytic refining. The word electro stands for electric current and lysis means splitting. The crude metal is refined by electrolysis, which usually consists of an anode, cathode and an electrolyte. We always have to remember the anode will be rods of impure metal being used, cathode will always be thin strips of pure metal, and the electrolyte will be aqueous form of the salt of the metal of interest. The metal of interest dissolves from the anode and passes into the solution, while the same amount of metal ions from the solution will be deposited at the cathode. During electrolysis, the less electropositive impurities in the anode settles down as anode mud, which can be removed. We have already seen the electrolytic refining of aluminium by the Hall-Herold process. Now let us understand this process, electrolytic refining, by considering silver as an example. The anode consists of impure silver rods. The cathode consists of pure silver, while the electrolyte is acidified aqueous solution of silver nitrate, AgNO3. When current is passed through the electrodes, the following reactions take place. The reaction that takes place at the anode, positive electrode, where oxidation occurs, will be Ag in the solid state gets oxidized to silver ions, which goes into solution by losing the electrons. The positively charged silver cations migrate towards the cathode and gets discharged by gaining electrons and gets deposited on the cathode. Other metals such as copper, zinc, chromium, etc. can also be refined by this method in a similar manner. Thank you.